Welcome back. In this video, we're going to look at a talk by Irene Schulman and Neil Spring about outages in last mile networks, specifically weather-related outages. As always, we're interested both in the results that they observed, but also in the methodologies that they used to measure the network. As we've said before, residential networks are notoriously unreliable. There's no redundancy in the system, and there are many sources of failure. From the most mundane users turning off their equipment, to trees taking down power lines, backhoes digging up buried fiber, power surges, lightning strikes, equipment crammed into small metal boxes and overheating, and the list goes on and on. But in particular, there are a number of weather phenomena that stress and therefore increase the rate of failures in these residential networks, including lightning, water, and wind. To make matters worse from a provider standpoint, many of these effects are transient. So the water that seeps in and disables some equipment may dry out before it's able to be observed and the equipment return to operating. Others of these are more permanent, such as lightning striking and frying equipment, or tree limbs coming down and breaking above ground wires. So why do we care about these failures? Well, for one thing, it's routine. Weather isn't going away anytime soon. So understanding the severity and impact of these outages helps us understand how well served the general population is by these last mile services. It also helps us understand the implications of services being converged on top of the internet. For example, when the phone service and the internet service are independent, there's a chance that one will go out and not the other. However, if the phone service operates over the internet service, then if the internet is out, so is the phone service. And of course, there tends to be greater need for emergency services during weather events. So it's increasingly important that the phone service remain operational even when there's other outages such as power or internet. So how do we go about measuring these failures? Well, the first step is identifying residential ISPs that might be subject to weather. We're not trying to measure the core of the internet in this case, and equipment in large data centers tends to be much less susceptible to weather outages than the equipment in residential networks. Once those IP addresses are identified, the researchers can use ping before, during, and after an event in order to observe any effects. And then for that observation to happen, the collected data must be analyzed. There are many different ways to go about classifying IP addresses to try to understand their purpose. In this case, the authors used the DNS. So they queried pointer records for different IP addresses and found words that tend to be indicative of the purpose of the IP address, such as pool, often referring to a DHCP pool. And we see later in those strings the term DSL. So we can infer that these IP addresses are assigned from a DHCP pool running on a DSL network. And we see that the syntax for these changes across providers. So different regular expressions are needed to process the pointer records from different providers. So these addresses then become candidates to ping. And we see that there were 100 million of these addresses discovered. So a brute force approach here would be to constantly ping all 100 million of these addresses, but that would waste a lot of measurement, effort, and bandwidth. So the researchers narrow down their measurement to places where weather is expected. They do this by monitoring the alert feed of the US National Weather Service, which contains certain keywords as well as geocodes. So the alert has a specific start time and stop time and indicates the geographic area affected. But we're not there yet. We need to take those 100 million IP addresses and figure out where each of them is located. For that, the authors used the MaxMind database of IP to geolocation, which we've also discussed in this class. And then they take a sampling of IPs covered by a particular weather alert. So 100 IPs from each provider and link type. Again, they're using the DNS to indicate the provider and the type of link associated with each IP address. So now that they have a target set identified, the next step is to ping before, during, and after the weather event. In order to do this, they use Planet Lab vantage points, and they're doing fairly infrequent pinging. The justification for this was fairly thin, but the idea is that multiple pings from a particular address within 10 minutes might trigger certain types of attack detection software. And so spreading the pings out to once every 11 minutes mitigates the potential for any complaints to come back about this study. Needless to say, if an IP address is not replying before the weather starts, there's no need to ping it continuously throughout the event. But for devices that have responded, missing a single ping is not enough to indicate failure. There's lots of reasons why a ping or a ping reply could be lost in the network. One of the reasons for the ping to be lost is due to how ARP works on routers. It turns out that when a packet arrives at a router and the next hop MAC address is not in the router's ARP table, it will drop your packet while it goes through the ARP process. So we see that while in most cases, the first ping in the interval is the one that receives a response, for IP addresses that respond at all, there's a significant fraction that don't respond until the second ping, due to the first ping being lost while the ARP lookup is happening, and that ARP table having been refreshed by the time the second ping arrives at the router. So once we have the responses from these pings, then the analysis comes into play. So the authors don't just rely on the predicted weather to indicate what was going on in these locations. They want to look at weather reports from actual weather stations. These are frequently located at airports and include things like lightning detection and identifying precipitation, as well as the accumulation of precipitation. So gathering the history from Weather Underground for a particular location, we can see the progression from clear to clouds to haze to thunderstorms and rain, light thunderstorms, heavy thunderstorms, etc., as well as the corresponding timestamps for each of these observations. So here we have a sequence in time of pings being issued from different vantage points, and also a heat map based on round trip time. And so we can see that some of the vantage points are simply further away from the target than others. But in this case, it's pretty clear that the target device becomes unresponsive just after the first hour mark and remains unresponsive until about the 9-hour mark. So that device was clearly out. We're still just dealing with a correlation in that the user could have just turned off that device at that time and turned it on 8 hours later. But if we look at this and it's correlated across 100 devices in a particular area, then we have a pretty strong argument that there was some sort of network outage there, not just in individual users turning off their devices. However, we have other types of results. This one the authors refer to as hosed, where the device goes from responding to all the pings to not responding and then responding to pings intermittently, but other pings are getting lost, and then eventually comes back up in a stable state. So in this case, it looks like there's severe packet loss on the network, but the device is still out there responding to pings as it gets them. So the authors performed this study during Hurricane Irene. And so they're able to provide this heat map showing the hosts that were up and down, and in the rectangles showing the reports from airport weather stations. And so we can see the clusters of down hosts on the East Coast at the same time as the weather stations were reporting significant amounts of rain. Beyond looking at outages on an anecdotal basis, we can also collect some broader statistics. So the authors categorized the providers by known link types, so they have cable, DSL, satellite, and fiber. And they computed the number of up to down events observed for each provider during the observation time. And they also categorized these results by weather event type. There, now you can see the thunderstorm graph on the right side of the screen. The green providers are cable, yellow to brown are DSL, blue is the satellite ISP, and red is the fiber ISP. So probably as a surprise to no one, the satellite provider has by far the most outage events, since those links are the most susceptible to different sorts of interference and obstruction. We see that the reliability of cable and DSL are comparable to one another, but vary significantly by provider. And maybe of interest is that the fiber ISP is not significantly more reliable than the other technologies. So for reference, here we've drawn a line showing that if we project out this rate, on average, it would result in an outage once every 35 days. Then we can see that during rain events, we have about double the outage rate. And during thunderstorm events, we have about 4 times the outage rate relative to the outage rate on clear days. So one thing that cannot be determined from this measurement methodology is whether the outage is due to purely a network failure or whether it's a network failure caused by an underlying power failure. So one thing that the authors discuss doing in the future is collecting information on localized power failures and correlating that with the outages they observe in the network. Also, because these measurements are end-to-end, it does not necessarily mean that the outage happened in the last mile, even though we assume that the last mile is the most vulnerable to weather events. That's all for this talk. We hope you found it useful, and we'll see you on the next one. We hope you enjoyed this video. If you found it to be useful, please click the like button. To be notified when more videos are posted for this class, please subscribe to our channel and click the bell.